A survey found that 17% of US adults say that Google News is a major source of news for them. You randomly selected 4 adults and asked them whether Google News is a major source of news for them. Find the probability that exactly 2 of them answered yes. Okay, so notice the wording here. We want the probability of exactly 2. So in this case, this can be thought of as a binomial probability if we say a success is a person answering yes, it is a major source of news, and failure is a person saying no, Google News is not a major source of news for them. So I've defined my success and failure, so now I would want to define my variables. How many trials are being conducted? How many times am I going to ask? I'm going to ask 4 adults. The probability of success, if success is them saying yes, that probability is right here. It's 17%, which is 0.17. The probability of failure, I always do 1 minus that number. So that's going to give me 0.83. And my X value, the number of successes I want, is exactly 2. So now I go to my formula. I substitute in my values. So I have 4C2 times 0.17 to the second power times 0.83 to the 4 minus 2 power, which is going to be 2. I'm going to type that into my calculator, and that should give you an answer of approximately 0.119. In number 2, it says, what's going to be the probability at least 2 of them respond yes? So I need to think about what outcomes would mean at least 2 said yes. Well, if there's 4 adults, that could be getting 2 people to say yes, or 3 people to say yes, or 4 people to say yes. So the probability of at least 2 successes will involve me finding the probability of 2 successes plus the probability of 3 plus the probability of 4. Now, I already calculated P of 2 in the last example. That was 0.119. To calculate P of 3, again, it's just a matter of going back and changing all the 2's to 3's. And then for P of 4, it's the same thing, but now swap in a 4 for your number of successes. Once you simplify these exponents, this is going to be to the first power. This is going to be to the 0 power. You're ready to go to a calculator and get your final answer. And when you do that, you should get approximately 0.137. And fewer than 2 say yes. Okay, what outcomes would mean fewer than 2? Would mean less than 2. If I want less than 2 people who said yes, either I want 0 people to say yes, or I want 1 person to say yes. I do not want to include 2, however, because fewer than 2 must be less than 2. So to calculate the probability that fewer than 2 say yes, I need to calculate the probability of 0 plus the probability of 1. I've substituted into the formula. So again, once you simplify your exponents, 4 take away 0 is just going to be 4. And 4 take away 1 is going to be 3. You're ready to put these into a calculator, and you should get approximately 0.863. Now, you could also have gotten this answer another way. Notice, if I'm taking a survey of 4 adults, the possible number of people who could say yes is 0, 1, 2, 3, 4, meaning my entire sample space has been used between parts 2 and 3. So I could, if I wanted to get the probability of fewer than 2, I could have done 1 minus the probability of at least 2 people saying yes. And notice 1 minus 0.137 does give me 0.863. So another way to do part 3 is to think of fewer than 2 as the complement of at least 2 and calculate it that way. Just like the last section, we had formulas for the mean, the variance, and the standard deviation for probability distributions. We have formulas for binomial probability distributions. But the good news is that we could use those same formulas from the previous section. However, because binomial probabilities tend to have nice properties, we can actually simplify the formulas. And notice how simple these are. If you want to find the mean, you can just take the number of trials you're conducting times the probability of success, and that will give you the mean. Variance is just n times p times q, number of trials times probability of success times probability of failure. And standard deviation, you just take the square root. So this is a much simpler process than using the formulas from the previous section. And again, this will only work for binomial probability distributions. So in example 8, we're talking about Pittsburgh, Pennsylvania, and apparently, depressingly, 56% of the days in a year are cloudy. We're going to find the mean, variance, and standard deviation for the number of cloudy days during the month of June. Determine any unusual values. Okay. I need to think about if I'm going to use these formulas, I need my N and my P and my Q. So I need the number of trials. Now, I'm only doing this for the month of June. You need to know how many days there are in June. Well, there are 30. So there's going to be 30 trials here. I'm going to look at 30 different days in June. P-value, the probability of success. Well, I'm going to, off to the side, define my success as a cloudy day. And this is what I mean by success doesn't always have to sound like a success, right? Most people would probably prefer sunny day there. But I can call success being a cloudy day, and I would then call failure not having a cloudy day. So my probability of success, my probability of a cloudy day is 56%, also known as 0.56. And I can get my Q, my probability of failure, by doing 1 minus my probability of success, which gives me the value 0.44. And then once you have those 3 values, you can calculate these 3 statistics quickly and easily. So here we go. For the mean, the only thing I need to do is multiply the number of trials I'm looking at times the probability of success. So I'm looking for 30 days times 0.56 successful cloudy day, and I get the average to be 16.8 days. So on average, I can expect to get 16.8 cloudy days in the month of June. All right, let's calculate the variance. The formula up above tells us exactly what to do to find the variance. Take N times P times Q. So I'm going to multiply 30 times 0.56, which I already did in the last example, by the way. And now I just need to take that number and multiply it by 0.44. And that'll give me approximately 7.4. But keep in mind, because variance is always measured in square units, this is technically days squared. This is why we don't like variance as a measure of how spread out the data is from the mean, because it's in square units. So the last step is to calculate the standard deviation. We're just going to take the square root of what we got for n times p times q. Again, not using a rounded value, so I want to make sure that on my calculator screen I have 30 times 0.56 times 0.44 and put all of that under a square root. And that's going to give us approximately 2.7 days. And that's telling us how spread out the data is from the mean. Now, the second part here, it says determine any unusual values. You need to know the definition of an unusual value. So any value that we're going to call unusual, these are the values that are more than 2 standard deviations from the mean. And so what you need to think about is you have this mean, and I like to think about it on a number line. It's just one way to look at it. If my mean is 16.8 and a standard deviation is 2.7 days, I can add that 2.7 on to figure out the number that would be located 1 standard deviation above the mean. And again, this is my mean. So 16.8 plus 2.7 is 19.5. And then if I add another standard deviation on, I get the number 22.2. Any number of days that's beyond this, that's more than 2 standard deviations away, would be unusual. So that would mean for this particular situation where we're looking at days in June, a June with 23 cloudy days or more is unusual. And I went with 23 because that's the first number larger than 22.2. But it's also an unusual value if it's more than 2 standard deviations below the mean. So I'm going to work backwards from the mean now, and I'm going to subtract 2.7. So 1 standard deviation away would be 14.1 days. I'm going to subtract another standard deviation. And 14.1 take away 2.7 is going to be 11.4 days. So here's my mean. 2 standard deviations above was 22.2, and this is more than that. 2 standard deviations below is 11.4 days. And these values out at this end would be unusual. The first number in this shaded area would be the number 11, because keep in mind 12 would be off here to the right. So we can also say a June with 11 cloudy days or less is also unusual. So again, this is one of the uses of standard deviation, is it can tell you which things occur very rarely. So please make sure you're familiar with this definition for unusual values.